Alright, so we're back on. Okay, so for the equation of a line in 3 dimensions, this is not going to be y equals mx plus b. Although, how far does it move away from y equals mx plus b? That's a good question, isn't it? Because y equals mx plus b was good in two simple Cartesian coordinates, y and x. Okay, very straightforward. Okay, but once we move across to 3D, how does that unpack? And that's really what we're doing. So what it does, it uses a parameter. Okay, but we'll get to the parameter in a moment. So we'll just put that there just as a reminder that we'll be using a parameter to help us with this. So again, you're given an example where we're talking about the example and just introducing a couple of ideas. So find the vector equation for the line that passes through a point and is parallel to another vector. So if we think about this from the point of view of 2 points, we could do that from the point of view of 2 points. If we were to think about just having 2 points, right? So out the back here's some p, and out the front here's some q. We could think about p to q as a vector, and we could say p and q are a vector. So what's the difference between what we're talking about here and the p to q idea? Because that's a line, isn't it? P to q is a line. So what it's doing, it's saying, well, the line isn't just the vector, it's all this. Now in terms of matrices, we could think about the displacement along the line, but we'll leave that for the moment. Alright, so there's a slight difference because we're just saying, well, what about if I want to come out here beyond P? Or what if I want to be here beyond Q? Okay, so we're nominating some point P to help us understand that there's a vector that's parallel. Now what is it about the parallel nature of vectors? Well, the parallel nature of vectors is going to help us, if you like. Here's an example. Here's your blue line with all the points on it, all the possible points on the line, and here's your parallel vector. We can use the information about both of those to help us establish an equation for a line anywhere on the blue one. So that's effectively what's happening. Alright, so so for different values of our parameter, we get different points. And so x is 7, 1, so that's all the way down here. So OX can be made up of OP plus 2 lots of the vector. So that's how we can arrive at x. How did we know it was 2 lots of v? How did we know 2 lots? Why not 1 lot of v? How do all 3 lots of v? So in this case it's given information. Okay, so OP is what we call a position vector to a given point. So there's our OP, it's a position vector, and the component form of the position vector, or the unit form for I and j. Okay, this is just swapping between unit form and component form. And it tells us the direction of the line. We add scalar multiples of v onto OP to get us to other points on the line. Okay, so in this case here we said it was, for example, 2 lots of v to get us to the other points on the line. Okay, so in concept, probably not such a bad idea that we've got a position vector, and then if we sum scalar multiples of the parallel vector, we can get to any point on the line. Because it's parallel in nature, it's going to take us in the same direction. This parallel vector, even though it's all the way over here, nothing to do with us on one level, because it's pointing in the same direction because of its parallelism, we're always going to end up on the blue line somewhere. So that's helpful information to know. Okay, so then there's a generic form of the equation. We've got our direction vector summed with some scalar of our parallel vector. That's what that means. Our direction vector summed with some scalar times the parallel vector. Now t here is your perimeter, and this is going to be our new point, our new vector OX. This is called the vector equation of the line through point P in direction of V. Okay, so how are we feeling about that? How are we feeling about having a direction vector, then having another vector give us the same direction, so that when we take off from P, we fall on the line of interest. We fall on the line of interest due to the fact that this is in the same direction. So whether we go that way or that way, we're in the same direction. Are we happy with that? Yep. Okay. All right. In this example, we've got OX, and now what we're doing is we're putting together the general form of this concept. So this equation here, as it's applied to this example, is the example form of this generalized form here. Okay, so this is very important. So this guy up here is the same as this guy here. It's just now this is specific too. So what have we got? We've got our direction vector. We've got some scalar multiplied by some other vector that's parallel. So when we do our addition, our vector addition, that's what that plus is, we're going to be on the same line. We're going to be on the same line. Okay, so in this case here, our original point was OP. Our original P is at 1, 5. So that's our component form of 1, 5. Then we've got the parallel vector. In this case is given as 3 minus 2. And so T can be used to help us arrive at any point xy on our point from OP, along P. So these are the parametric equations, and x is defined as that pair, the x pair, and y is defined as this pair. Okay, so that was just an example. Alright, let's have a look and see if we can do that. How would you find 2 more points on a line? Simply by changing the perimeter. So simply by changing the perimeter. So in this case here, let me do it this way. So we've got xy is our 1, 5 plus t 3 minus 2, which was our parallel vector. Put a squiggle under that, parallel vector. And then we're told about this component form. X is equal to 1 plus, so if we expand that and do that, that's a pair. 1 plus 3t. If we expand this one and do the second point, that's a second pair, y. So this manipulation from this form to this form and back again is what this topic's all about. And it's as simple as that. If you can manipulate the forms and get them back and front, you can find out, if you're given the parametric forms, you can work out what the parallel vector is. If you're given the parallel vector, you can work out what the parametric lines are. Okay? Alright. Simply by changing t, we can move to points on the line. So that's good. 20 minus 3, is that on the line? So we've got our equations, and so what we're doing here is we're rebuilding them. We're given values and we're putting those in and checking them. Okay, now if t is different, if t comes out to be different, see how t is different for the two things here? Then it's not. T should be the same. The t that we generated here should be the same. So if the point's on the same line, then the t that we get in reverse engineering, okay, so when we put 20 in as x and minus 3 in as y, when we reverse engineer it, this t here, they should be the same. That t and that t, they should be the same. But because they're not, then this doesn't make any sense. And that 3 there is really a sensical kind of thing. It's saying, oh, Well, if 20 and minus 3 are on the line, we'll get the same t. So you might want to make a note here. This is where you have to write something down. If a point lies on the line, when you reconstruct x and y parameter equations, you get the same t. Alright? When the point is on the line, when you reconstruct the parameter equations, you'll get the same t. That's all that example 3 is doing. You're getting the same t. Now we can take this off to 3 dimensions, but the concept doesn't change. There'll be a parallel vector that tells us to go in the same direction, and so find a point. And if we're reconstructing any of the x, y, z equations, then the t should be the same. Alright. Now, that's tricky. How are you feeling about that? Right, that is tricky. Okay? But this is the form swap. This is all it is. This is the key to it. Okay, if you can get used to that, then we can process it. Similar kind of thing when you've got x, y, z. You've got your common t. You've got your parallel vector. There's your parallel vector, a, b and c. And you've got the point that passes through. Remember that the parallel vector doesn't have to be on the line. It's just got to be parallel to it to get you to go in the same direction as it. Of course, that's the thing. So it's like a bit like having someone over there shouting, go that way, so that you find the point on your vector. Because they know what direction they're in, which is the one you were after. So the general form of the equation is not changed. We've got our direction vectors to start off with. Then we've got some scalar that we multiply by this direction vector, which will help us go in the same direction along, multiplied by t, and so we'll get a new addition that will give us the point on the line. Now if we eliminate t, so that's just looking at these equations from the point of view of not looking at t, how would we do that? How would we eliminate t? We'd solve t for each one, wouldn't we? So just very quickly, if we've got xo plus at, solve for t. So you'd put that over, so you'd have x minus xo, that's moving that over, equals at, and then you divide by a, wouldn't you? Okay, and then we can do it again for y and z. So you get the same thing. Okay, they'd be all equal to t. That's all that's happened there. Okay, just to get rid of that comma. Alright, any questions about that one? Because I think we'll move into some examples now. So you've got some cross product, you've got some dot product. That's an example there. This is one I think Denita would have done some years ago. Find the vector equation of a line that passes through the point and is available to V. So the general form, let's have a look. No, do a 3D one. We'll do the 3D one. So the point is 632. The parallel vector is 2i plus 4k minus j minus 2k, or in component form. Okay, so then our basic form of an equation is what? Let's go back and pick up the basic form. I could have scrolled up, but I won't do that. That's the basic form. So essentially, in order for this all to make sense, we should have the new thing that we want to do is the result of our direction vector plus some scalar plus our parallel vector. So what do we expect to put in? Well, we're going to put in our unknown t, our 6, 3, 2, the point has a vector from the origin, that's our position vector, plus t, and then we've got our parallel vector. Now that step there, folks, is the big step. That's huge. Okay, that's huge. And then the next bit we did previously, when we did this little step here, we see this form to form to form. So all we've done is generate that, and then the form to form we want to generate x, y, z. So we've got to do these expansions. Okay, so to get your expansions, we're going to go for x, which will be 6 and 2t. That's that expansion. For y, what's it going to be? Anybody help me out?
Will it be -3 plus 4t?
Genius. That's all it is. Okay, and the final one will be 2. Now, that's a -2, so it's going to be -2t. So we've got them in parametric forms. Okay? So it wants the vector and parametric equations, tick. So that's our vector equation. And that's our parametric equation. Whether it's 2D or 3D, it's the same idea, isn't it? And then it says find 2 other points. So for finding 2 other points, so that was A, and then B says find 2 other points. What 2 other points? Well, you decide. You can make it up. You can make it up. So what would be the t? In the example that's on the screen there, 1 and -1. And so if you substitute t into those, you'll get x is 6 plus 2, which is 8. You'll get, sorry, I'm going to put it as a point, not a vector. Well, I could put it as a vector. Wouldn't matter. Wouldn't be wrong, but just to be consistent. Any other point on the line, so I'll just rub that out. It's not wrong, because we know we can go from the origin to the point, but I'll put it in as a point. And I'm doing this in my head slow-mo. -3 plus 4 ones 4. So -3 plus 4 is 1. And finally 2 minus 2 would be 0. So that point is on the line. And -1 now. So 2 times -1 is -2. 6 minus 2 is 4. 4 times -1 is -4. -3 minus 4 is -7. And -2 times -1 is +2. 2 plus 2 is 4. So that point is on line. Two more points that are on the line. Okay. All right, so I encourage you to think about that. All right, are there any other questions? Because I think we've pretty much got all of your videos sorted. That should all be making sense to you now, I hope. So this is the place where you can, if you've got a particular question that you're not sure about, how did that work? Okay, and hopefully the tutorial made sense to you when you went through the tutorial. Using just your basic algebra, and the next tutorial will have these dot products and cross products, equations of lines and the like in them with they. So what I'm trying to do is help you what to expect and how to conquer it. Right, is there anything else that we need to look at from that point of view, or are we happy to kind of move on? Which brings us to the end of effectively to the end of that part. So any queries here from the practice questions that you got? Anything crop up for you from that lot? And then you had your tutorial as well. Oh, you got your solutions for tutorial? Because I'm looking at this as a matrices, so your beginning matrices. So what I want you to do is really you should have worked through your tutorial and any of these practice questions. All right, was there anything in any of that that you found you wanted an explanation, or are you happy with that?
If you could maybe work through one of the tutorial questions in the modeling B section.
So this tutorial here.
Yes, I believe so.
Alright, so let's give ourselves some space. And so we go down. Modeling B.
Yep. And question 1 in that. Oh, sorry, question 2. I managed to sketch it, but yeah, I just wanted to go through and make sure I'm right.
No, that's fine. Okay, so let's have a look at it. Alright, so we need to use information from here. So let me just write that information down. Okay, so they're all sitting on axes. How do I know that? Because that one's not. They're all sitting on axes because this should be fairly easy to draw. A is 2, 0, 0, so A is there. B is Y, so it's there. C is on Z, so this is a tetrahedron. This is what's called a tetrahedron. And so if we just draw that line across and that line across, this is a classic kind of shape that gets used. Sorry, I missed that point. 2, 2. Now where's 2, 2, 2? 2, 2, 2 is going to be out here somewhere. So if I had to draw it up, two, 2, 2 is going to be up here somewhere. Sounds like a little ant, doesn't it? So that's our point 2, 2, 2. Okay, so that should be it. Now 2, 2, 2 is not necessarily sitting on top of the tetrahedron, but it wants us to know what the angles are. Alright, so for C, for D, so it's going to form like a pyramid, isn't it? It's going to be like a pyramid. I mean, that doesn't do it justice. So that's better. It's a bit more readily to see that that's a pyramid shape on that. Alright, so that's enough of that. Okay, so the question's saying find the angle between CA and DA. So this is where you need your point-to-point building skills. So CA is a vector that we need to establish, and we're going to go to the second one, and we're going to put 2 minus 0, and then 0 minus 0, and 0 minus 2, and so for all of that we'll get 2, 0, negative 2. Are we happy with that? That's our point-to-point vector for that one. The other one we want is D to A. So we go to A and we subtract from C, so we've got from D, so we've got 2 take away 2, 0 take away 2, and 0 take away 2. That's our going to A and then subtracting, so we'll get 0, negative 2, negative 2. Now in some way these space vectors are sitting however they're sitting. We know vectors can go all around the page, right? Okay, that's the first thing. Now the thing that will help us with the angle is the dot product. Now the dot product has a couple of different forms of an equation. CA dot DA is the component forms equal to the magnitudes times the magnitudes. So I'll have to work those out by the look of it. And then the angle, the cosine of the angle between them. Is that right? So in essence I put all the elements in, I think. So I can do that. 2, 0, minus 2. Now we need to do both of them because the unknown here is this. So we actually need to do the sum of products. So 2 noughts are naught. What am I doing? The sum of products is going to give us a number. See how easy it is when you're switching around? 2 noughts are naught. Sum of products, naught. Minus 2 times minus 2 is plus 4. So the component form gives us a 4. Now to do the length, that tells us to do the length. So we've got 2 squared plus. Now anytime you're not happy with something, let me know. That's the magnitude. Use of brackets. So what do we end up with here? 4 plus 4 is 8, so we get the square root of 8. And 4 plus 4 is the square root of 8. So we've got 2 square roots of 8. So we've got equal to the square root of 8 times the square root of 8 cos theta. Now, those squares are going to do what? I might just do it this way. Okay, that's better. Now what's this going to mean? They're going to disappear, so we've got 4 is equal to that's beside the point. What do? We times them, So we're going to get a to the power 1. Okay? So if we look at it through that lens, so we're just going to be left with 8 cos theta. Does anybody disagree? So we divide by 8 both sides, and we'll get cos theta is equal to a half. Now, you've done with me your exact values trig. So before I go any further with the calculator, which I could do, what's that look like? Well, what's it asking? Come on, exact value trig me. Exact value trig me. It's asking the value of x is plus a half.
Yes, when x is a half.
The value of x is plus a half. So we're going to come along here to a half. Alright, and we're going to have these, aren't we? Now we could count around, and we'll see which theta makes sense. So on this angle here, theta would be equal to the larger angle, which has the smaller denominator. Yeah, remember that? Larger angle has a smaller denominator. Now, why isn't it this one as well? Why isn't it this one? I mean,
because that would make y negative?
Yeah, y would be negative. Okay, so that would kind of take it out, wouldn't it? Okay, so we only want the positive one. But just keep in mind 1, 2, 3, 4, 5. You know, 5 lots of pi on 3, but we only want the positive one. Okay, just keep that in mind whenever you're doing that. Now, the other thing you can do, of course, is do cos to the minus 1 of cos, which is undo, is cos to the minus 1 half, which you'll now need to do if you want to do it that way. But I've just shown you how to do it without a calculator, but we'll do the calculator because we're being dangerous. So 1 divided by 2 is 0.5, I know that. Now in terms of trig, we can go second function cos, and it's 60 degrees, that was a good one. If I change that to radians and do second function, oops, I better clear that. I don't know how to get the 0.5 back, I've never worked that out. So trig second function radians cos 1.047. So what you've got to do to satisfy yourself of that is go pi divided by 3. Okay, it is pi on 3. That's why I don't like using calculators, because I feel calculators take away. Alright? I feel like they take away. We know that's 60 degrees from our exact values trig. But we know that's 60 degrees from that one. So what's the angle between... Oh, there it is. We got it. The angle is 60 degrees. Okay, so that's just manipulating the dot product, wasn't it? Alright, any others? Or does that mean you want to work on the rest yourself? Because the next one's the same problem. It's just using the dot product unpacked. It's just using the dot product unpacked. Nothing tremendous there. It's showing the angle is just getting the carbon atom at the centroid. So that's a repeat question. Okay, so what this is doing is assuming that because you've just done a similar question, okay, because you've just done a similar question, that you're going to be able to reconcile that this centroid D was at 222, and so it had A, B, and C vertices at 2 zeros, blah, 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 you're going to be able to reconcile, because you've done this example with a limited amount of other information, that you're going to have 1, 0, 0, 0, 1, 0, 0, 0, 1, and your centroids at 1, 1, 1. You're going to repeat the question exactly as we did here, and instead of having 2s, you're going to have 1s, all right? And you're going to find out what the angle is, and the angle is going to confirm that point there. So it's exactly the same thing. It's just that abstraction, isn't it? It's just that university abstraction. Saying, hey, you did an example, now do another one. This time the scale's different, that's all. Okay. I like some of these. Some of these get pretty good. Collinearity. What does collinear mean? Collinear means they're on the same line. So that's your points. That's your points with a scalar, some multiple scalar. You've done that with points on a line. Yeah, there's a lot to take in today, so I'll let you. Now, I showed you guys the integration table inverse, didn't I? I did that with you. I computed the derivative of the inverse.
Yes,
yeah,
I think so.
Yeah, I'm kind of inclined to keep hitting that because it's important. But what we'll do is we'll leave it there, I think, unless you guys have got any more particular questions. Well, I might leave it there. And hopefully you found that the same approach works with vectors. It doesn't matter what the topic is. The approach works, I hope. I hope you're feeling that still. I hope you're feeling that you know how sessions are worthwhile. Alright, let's pause there. And that's been 2 solid hours. So thanks for coming along, guys. And I'll see you next time. I'll post the video and the working sheet, and then you can go through that as you wish. Okay? Alright, thanks guys. Thanks for coming. I'll see you
Thanks, Jason.
See you next week. Bring questions if you have them. Yeah.